In this session, we are going to talk about estimation. And from previous session that we have established all the terminologies and the linear model that we have. So here we're going to estimate the value for the coefficient beta 0 and beta 1 in the simple linear regression model. And we know those two parameters are unknown, and we are going to use the data we have to do the estimation. And I have put here, we will use the sample of the data we have to estimate the population level values, because this beta 0 and beta 1, they are the population parameters, and they are definitely unknown. And we estimate these values by finding the equation of the line that best fits the data. And choose the intercept and slopes of the line as our estimate. So this beta 0 is the intercept, and the beta 1 is the slope, as we mentioned from the previous session. And the goal here is to find B0 and B1 as the estimate of beta 0 and beta 1, so that this yi hat equal to the summation of B0 and B1 xi is as close to yi as possible. So that's what we mean by this best fit. And yi hat is the befitted value of yi, so we put a hat on it. And the value of the line of the best fit at x equal to xi. So whenever you see there is a hat here, that means that's an estimate, that's the predicted value or fitted value for the yi here. Okay, this is I will show you with this little example to show you how do we get the best fit. So from here we have 6 data points, and I have labeled the residual, the ei hat. So this is the difference between the actual value of y and actual value of yi, and the predicted value of yi hat. So the distance between these two, we call it residual, and we want to minimize those residuals so that the data we have, the line we estimate will be as close as to those data points. So each of this dot here is one of our data points. I said here in this plot, the line of best fit for the hypothetical data is drawn is here. The residuals are shown as a difference between the data and the actual value y and the predicted value on the line. So this is predicted value as the difference between the actual value of y and predicted value on the line. So this line is our fitted line. So these are the predicted value, and these are our data, actual value of y. Okay, and when we add those values up for the residuals, that's how close our prediction are to the actual values. And one of the most common way to calculate B0 and B1 is called method of least squares. And these are the mathematics we use to do the estimation. This previous slide is just showing you like intuitively how are we going to find this line, but eventually we would have to use math to do the calculation. So in the least square, in the method of least squares, B0 and B1, I mentioned this are the estimates for beta 0 and beta 1, and they are chosen to minimize the sum of squared residuals. So note that the sum of squared residuals, we use RSS to denote that. So this is the summation of the residual squared residuals. right? So explicitly we write it out, which is yi minus yi hat. This yi hat is the fitted value, predicted value, and this yi is the actual value in our data. And to further write it out, this yi hat, it's just b0 or estimated intercept, and b1 times xi. This b1 is our estimated slope. So the sum of squares residual is also called residual sum of squares. But anyway, we just use RSS to denote this quantity, and our purpose, our target is to find the minimum with respect to the minimum of RSS with respect to B0 and B1. And so we take the, so this RSS is, you can think it as our target function or objective function. And we're going to do to get a minimum with respect to this two unknown values. So we take the derivative of this RSS with respect to each of them and set them equal to 0. Well, if I remember correctly, this method, like you take the derivatives and then you set them equal to 0, is called Lagrangian optimization. So it's a very common way that you do optimization, but here we are going to do a minimum. So take the residual, it will be like this, because like when you take take the derivative, you take this 2 to the front, and then this whole thing to the power of 2 minus 1, then it becomes this, right? And we set it to 0. So this is with respect to B0, and we do it again with respect to B1. And so when we do it with respect to B1, there is the extra xi came out because we have this extra term here with respect to B1 here. So this uses a little bit of calculus. Hopefully you are still familiarized with those. And then we do some rearranging for the two equations from previous slides. So it would be, the first one would be like this, the summation of yi being equal to this, and summation of xi and yi being like this. Remember that we are trying to get the value of B0 and B1. So that's why we rearrange it like this, and you solve for the equations. Okay, before that, this two are also known as, they are also called normal equations. Normal is a term in geology that means to be perpendicular. The least square residuals are normal to the space spanned by x. So we just got this term for these equations. Well, so we solve those normal equations, then we get the estimate of beta 0 and beta hat. And this is what they look like. And also this is a little messy, and so people tend to write this numerator and denominator as SXY and SXX. And I have said in the note here, they are common terms in statistics. So that's why like we gave them this short name. So where this SXX is the sum of squares of difference between each x and the mean x value. So it is x bar, and XXY is the sum of the product of the difference between x and its mean and the difference between y and its mean. So they are corresponding to this denominator and the numerator and denominator. Well, we talked a little bit about matrix calculus, and this is where we're going to use it, at least for this chapter. Previously, we went through how do we get the estimate of beta 0 and beta 1, use this calculus techniques. But here, when we write those equations into matrix format, it will be like this. Hopefully you will get used to this, because I think for the most complicated mathematical problem, it will be better that you write them out in matrix format, so that you do not need to really keep track of this this indices, like either use xi or whatsoever. At least personally, I feel this is really messy. When we do really formal inference, we use this matrix format a lot. And this is actually the simplest model we will discuss. So I think it's better that we go through this at this point, so that you can get familiarized with this notation. Yeah, let's get to the model, to the matrices. So again, this yi and xi are the same as previous defined. That's for each pairs of data, and beta 0, beta 1 the same. And we are going to write them out for n data points. So we just put them in order in a vector format for the y, and correspondingly we would have this beta 0, beta plus beta 1 times x1, and then x2, etc. to xn. So this just correspondingly for each of the y, and it will also, you will also need to sum up this error term where I use epsilon, epsilon I for I from 1 to n. So this is just explicit write outs for n data points, and then we reorganize this further. We get this y vector, and then we get a matrix of 1 with a vector of 1 and a vector of x. So this is an n by 2 matrix. We normally just call this thing as a capital X. So as if you correspondingly for each term, this vector of y, I use this capital bold y, and this matrix, I use this bold x, and this beta here is a vector of both beta 0 and beta 1, and this epsilon is a vector of this epsilon i's. And I also write out this dimension for each of these terms. So just for your reference, normally you do not need to write in this way. This simple one should be enough. Okay, so now we got the formula, the main model here, y equals x beta plus epsilon. And remember, we are going to get the sum of square residuals. So what is the residual looks like in the matrix formats? It's simply just y minus x beta, right? That's easy. And we take the sum of square residuals like this. But if we want to write them into matrix vector format, it will be a horizontal vector and this vertical vector. You just do the multiplication of these two, you will get the summation of the squared residuals, right? If you just do the calculation, this times this plus this times this. So that's how you do vector multiplication, right? And write them in matrix format. It's just epsilon prime, which is the transpose of epsilon, times epsilon itself. Yeah, and the epsilon here is this thing, right? Correspondingly with this epsilon is this vector. And we want to minimize this RSS, right? residual sum squares, it will be, we just write this epsilon odds, which is y minus x beta, and then take the prime and multiply epsilon again. The next step is to take its derivatives. Take the derivative of this whole thing. Well, you can write this odd, like the multiplication of this two thing. Well, yeah, I'd better just repeat it here, just in case you forgot. Like the prime of the whole thing equals to, like, take the prime for each. Like when you take the prime for the x, take the transpose for this x prime beta, then it will equal to beta prime times x prime, right? And then you do the multiplication, like term by term. You get an equation, and then you take the derivative with respect to beta. You will get this by using the matrix calculus that we mentioned in our previous session. You get this. This is your derivative, and we set it to 0 so that to estimate the beta. Eventually, we get normal equations as well in matrix format. Then it's straightforward how you get this estimate of beta being b equal to x prime x, and this is the inverse of x prime x times x prime y. This is something you should get yourself familiarized, because it's very common when people ask you what is the estimate of the coefficients for simple linear regression. You can either use like like this, something like this, like separately for beta 0 and beta 1 hat, or you can just simply see this is the our least square estimate for the coefficients of our simple linear model. And when we get to the multiple linear regression, we would still have the same set of the same set of matrices, and we will get exactly the same format here, but our x will just be a bit of different. So yeah, I think that's all for this session. And next time I will go through some examples of the simple linear regression. How are you going to apply this? Use R, and yeah, how are you going to build a model?